Hello everyone, my name is Pipin Abram, and in today's video we will talk about refraction through glass slab and the concept of real and apparent depth. So let's get started. Okay, so the first topic that we are going to discuss today is light ray, which is going to pass through a glass slab. So when the light ray passes through a glass slab, there will be some kind of shift in the image of an object. So that is something which we are going to study. How much shift is going to happen, that is something that we are going to study in today's video. This is just the first part of the video, and the second part of the video will talk about the real depth and apparent depth concept, right? Okay, now this is how a glass slab looks like. So this is basically a glass slab. I just made an image of glass slab. I'm sure you must have seen your glass slabs in your schools, right? Okay, so let's very quickly see what happens. Normally, let's say we will discuss the topic lateral shift. Now I'll talk about what lateral shift is. Now before, let me use an example so that it can get easier for you to understand. All right, so imagine that you are watching an object from your eyes. All right, obviously we'll use your eyes to watch an object, right? So what is going to happen, the normal process is that the rays reaches the object, right, and then it will come back to your eyes, and that's how you are able to see any particular object. Is that a yes or no? I hope you guys can understand it, right? Now imagine the same thing happening, right? So I'll just copy this entire image. So I'll just copy this, and imagine if there is a glass slab in between, right? So right now the same thing we are observing, right? The only difference here is that instead, so right now here you had simple air medium, there was no material to refract it. Now let's imagine that in between there is a glass slab of, let's say, thickness T is in between your eyes and the object, right? Okay, in reality, when there was no obstacle or when there was no glass slab, the image should be seen here, right? And that is very nicely, you can see it should be here. But now, as you can see, there is a glass slab in between, right? So very quickly, let me just make you guys understand all the concepts here. First of all, you can see the light ray is basically entering from your ear to glass slab. So glass slab is basically made up of glass, so it will have a refractive index of glass also, right? So you guys can see the light ray will be passing from air to glass and then back to air. So this is how it is going to happen, and we can very nicely see that obviously when I compare two mediums, for example, let's say this is my first interface, so you can see first it is air and then it is glass. So obviously when I compare air and glass, you can simply say that your air is a rarer medium and glass is a denser medium in comparison, right? Very similarly, there is this next interface, that is glass and air, right? Again, obviously glass is again denser when I compare it again with the air. I hope you guys can understand that, right? Okay, great. Now let's try to understand what is going to happen here, right? So the light ray will go like this, right? And you guys can see here is the point where it is like, it is colliding at the interface, right? Now this is the first interface, you guys can see this is the first interface, it is colliding here, right? So above this interface we have air and below this we have glass, right? Okay, now we already know the first thing that we have to do whenever we have an incident ray, let me call this as incident ray of light, right? Okay, so the first thing is that we will make a normal, right? So very quickly let me make a normal here, right? The moment you make the normal, then next step is that we will trace the refracted ray. So basically we are going from air to glass, that is we are going from rarer to denser medium. So when your light ray is going from rarer to denser medium, it is tend to bend towards the normal, right? So basically your light ray is going to bend towards the normal. I hope you guys can see that, right? So let me say this is your angle of incidence and this will be your angle of refraction here. Yes, I hope you guys can see that, right? Great. Now again, we are at the interface. Let me call this, okay, let me just say this is my A point, this is my B point, right? Again, we are at the interface. Next step is that very nicely I will going to make a normal here, right? So you have made the normal here. Now what is happening here? This is my next interface, and we are traveling from class to air, right? That is, we're going from denser to rarer medium. So basically, whenever light travels from denser to rarer, it tends to move away from the normal, right? Is that a yes or no? So basically, it is going to move away from the normal. Yes or no? Yes. So you guys can see it is going to move away from the normal, and this is your angle of, let me say, this is your angle of emergence. Basically, we call it angle of emergence, which is represented by I dash, right? This is your angle of emergence. So basically, with some angle it is coming out, right? So now you have to observe very carefully. Normally, if there was no glass slab involved in this process, then what would have happened? The light ray should have gone like this, and I should be able to see the image somewhere here. Yes or no? But as you can see, because of the refraction process, instead of here, I'm going to see my image somewhere here. Yes or no? I hope you guys can see, you guys can understand this concept. So let me just very quickly just copy this. All right. And yeah, so basically I'm going to see my image somewhere here, right? So I will not see my image here. I will see my image somewhere here, right? So there is a shift, right? There is a shift in the image. The image was supposed to be here, right? But you guys can see there is a shift in the actual image. I hope you guys can understand that, right? Now this shift is something which we can find out, right? So this is the shift here. If I draw a perpendicular here, this perpendicular is the shift, right? We call it P, right? Let me just call it P. Now this is what we call as your lateral shift. Lateral shift in the image. That is, your image is being shifted by some distance, and that distance is what you call as your lateral shift, right? Which is represented by the symbol P. Now we can very nicely find the value here. All we have to do is simple geometry we have to use in order to find that value, right? Right. Okay. Now this, what is this angle? This angle is what you call as your angle of deviation. This is represented by the delta symbol. Let me call it delta. This angle of deviation. Now what is this angle of deviation? That is how much your refracted ray is deviated from its original path, right? So you guys can see this was the original path if there was no glass slab, but as you can see, because of glass slab, the path is being deviated by some angle, and this angle is what you call as your delta, right? That is your angle of deviation. Yes? Okay. All right. Great. Let's move forward. Now this angle is 90 degree, which we already know, right? And let me just name few things. So let me say this point is D. All right, great. Now we can very nicely find out the angle. What is the value of angle of deviation? What is the value of angle of emergence? Now from this image, you guys can see, if you clearly see from this image, you guys can see this is your normal and this is your expected rate, right? Now if you see, your angle of incidence must be equals to angle of refraction and angle of deviation. Can you see that? If I zoom this out, then you can simply see this and this. Yes, these angles must be equal. Why they must be equal? Because of vertically opposite angles, right? So very nicely I can write it here that your angle I must be equal to angle R plus angle delta, right? Or you can see angle delta is basically equals to angle I minus angle R. I hope you guys can understand that. All right. Now let's very quickly apply Snell's law at A and B, right? So I'm going to apply Snell's law at A and B in order to find out few things, right? Okay. Now let me very quickly apply Snell's law at A. So let me first apply Snell's law at A. So if I apply Snell's law at A, you tell me what is going to happen. At A, I'm going to apply Snell's law. Let me say refractive index of air. Let me say it is some new one. Refractive index of glass is some new 2. Then again, refractive index of air is new 1. Now, let me just apply Snell's law at A. So when I apply Snell's law at A, I can simply write, yes, I can write refractive index of air times sine of angle I will be equal to refractive index of glass into sine of angle R. Is that a yes or no? I hope you guys can see that, right? So I'll just write that here. Refractive index of air times sine of angle of incidence will be equal to refractive index of glass times sine of angle of refraction. Is that a yes or no? Let me say this is my equation number 1. All right, great. Now I'm going to apply Snell's law at point B. Apply Snell's law at point B. So when you apply Snell's law at point B, what is going to happen? All right, so here you apply Snell's law here. So what is going to happen? You already know here. Okay, so now one more important thing before I do that, you tell me what is this value. This will also be angle of refraction. Now why it is angle of refraction? Because you have to see this and this, they are parallel to each other, and you guys can see this forms a Z sign. I hope you guys can see that. So these angles are alternate angles, right? So if this is R, then this angle must be R2. I hope you guys can see that, right? Okay, great. So now at point B, I can write refractive index of your glass times sine of angle R is equals to refractive index of air times sine of angle I dash. Yes or no? All right. This is your I dash, right? Okay, great. Now let me just write that thing here. That is refractive index of your glass sine of angle R is actually equals to refractive index of air sine of angle I dash. Is that a yes or no? This is equation number 2. Now very quickly, if I compare both the equation, just compare equation, right? So you guys can say nu2 sine R and nu2 sine R both are equal, right? Also nu1 sine. The difference is I dash and I, and you guys can see both the equations are equal, they can be equated. So by comparing these two equations, I can simply say by comparing these two equations, I can simply say equation 1 and 2, I can simply say that your angle of incidence is actually equals to angle of emergence. It must be. Then only these two equations can verify each other. Yes or no? So I can simply say from here, I can conclude from here that your angle of incidence is actually equal to angle of emergence. All right, I hope you guys can understand that, right? Okay, great. Now if it is understandable to you, now let's find a way to find out the value of lateral shift. Let's try to find out the value of lateral shift, right? Okay, in order to find out the value of lateral shift, let me just again make it so that it can be understandable, right? Let me just make it big so that it can be understandable. Okay, very quickly, let me just make it, yeah. All right, so this is the thing, right? Okay, now let me make the rays here. So we had a normal, so from the normal your rays are going like this, then again you have a normal here, right? Something like this, and the rays are going like this. All right, okay, something like this, and it should be parallel, something like this. Yeah, great. Okay, now this is your perpendicular, this was your A, this was your B, right? This was D. All right, okay, great. Now I can just extend this normal here till here. Okay, let me call this C. Okay, all right. So this was your angle of incidence, this was your I dash, this was R, this was R, all right. And this was delta, that is your angle of deviation, all right. Now if all these things are understandable, right? Now let's very quickly see in triangle ABD. Now what are your triangle ABD? This one, ABD. So basically you can very nicely see ABD is a right angle triangle at D. All right. Okay, so for that particular triangle, if I try to find out the value of sine delta, right, that is sine of delta, I'm talking about this one. So sine of delta can be written as, it's basically a ratio that is perpendicular upon hypotenuse, right? So for this triangle, as you guys can see, for this particular triangle, so when I talk about sine delta, that is perpendicular, which is perpendicular this one, this side upon hypotenuse. So this is your hypotenuse. I hope you guys can see, or I can simply write it here, BD upon hypotenuse is your AB. Yes or no? I hope you guys can understand that. Okay, now what is your BD? BD is your lateral shift, that is the value of P which we are supposed to find out, right, divided by AB. All right, great. Or I can simply say AB is basically equals to P upon sine delta. Let me say this is my equation number 1. Okay, equation number 1 is already used. Let me say equation number 3. Okay, now after this, let's talk about next triangle. Let me just say, use different pen. Okay, so in triangle ACB, I hope you guys can see that, ACB. So this triangle again, if you see, it is right angle at C. Is that a yes or no? It is basically right angle at C. All right, great. So for this triangle, if I talk about cos R, cos of R, so basically I'm talking about this angle. So normally I know the ratio of cos, that is cos is given as base upon hypotenuse, right? All right. So for this triangle, if you guys see, the base is basically AC. AC is the base and AB is the hypotenuse. I hope you guys can see, right? Okay, so your AC is the base and AB is the hypotenuse. Is that a yes or no? Right? Okay, now we already know this has a thickness of T. Now AC is basically the thickness, right? Because you guys can see this thickness and this is basically perpendicular. Basically these two lengths will be equal, right? Okay, great. T upon AC. Now AC is something which we do not know, or I can simply say, again I can write it here, my AB is actually equals to T upon cos R. Again, equation number 4. All right, great. Now if you guys remember, from here we got to know that your delta can be written as angle I minus angle R. Yes, delta, that is angle of deviation, can be written as angle of incidence minus angle of refraction. So what is going to do? So I'll just write it here. This AB can be written as P upon sine, instead of delta I will write it I minus R, right? From where I'm writing it here? This one, right? From this relation I'm writing it, right? Okay, so AB is equals to P upon sine I minus R, right? Okay, now all I have to do is equate these two. Just equate these two. So if I equate these two, I will get, very nicely I will get T upon cos of R will be equal to P upon sine I minus R. Now if you remember, I'm supposed to find out the value of P, that is your lateral shift. So that will be equal to, yes, P will be equal to T sine I minus R divided by cos R. I hope you guys can understand this, right? That is P. What is your P? P is your lateral shift. Lateral shift. Yes. So basically this image will be shifted by what value? It will depend upon T sine I minus R upon cos r. I hope you guys can understand that, right? T sin I minus r upon cos r, right? So very quickly, let's look at our next topic, that is concept of real depth and apparent depth. Now, let me give you a classic example. This is an example which is always, talked about when we talk about real depth and apparent depth. Imagine we have a tank full of water, or till this level, right, as you guys can see. So we have this tank full of water, and let's say inside the tank there is a material. Let's say, for example, there is a coin, right? And this coin, in reality, it is actually at the bottom of the tank, right? But let's say you guys are, here watching from your eyes. So when you watch, you will see there is some irregularities in your observation. What you will see that this coin, which in reality is basically placed at the bottom of the tank, you will see this is actually raised by some height, right? You will see the image is somewhere here. From your eyes, you will see that your coin, which you actually, intentionally kept it at the bottom, it is actually now here, right? So there is this irregularity. And why this irregularity happens, now we all know the answer to this question. It is because of refraction, right? Because the light obviously is coming from, from air to water. Because of the refraction process, you guys can see the image of this particular coin, which is in reality at the bottom of the tank, will appear somewhere here, right? Now let's try to understand what is real depth and what is apparent depth have to do with it, right? Now let's say, now this is the interface, right? So from the interface, the real depth or the real height of the coin is what you consider as the real depth, right? Is what you call as the real depth. And from the interface, the distance till you see your observed image, this is what you call as your apparent depth. All right, okay. So this is what is, and we will try to find out, is there any kind of relation between your apparent depth and real depth, and it has something to do with refractive index. We will try to find out, right? We are going to derive that, right? Okay, so let's start how we can relate between your real depth and apparent depth, right? Okay, now let me very quickly make this bigger so that this can be understandable, right? So let's say same thing, I'll just, I have just increased the magnification here, that's all, right? So again, you have the same tank, right, bigger in size now, and you have a coin which is sitting at the bottom, and you are watching from above, right? Okay, now so when you are watching from above, it's pretty simple. Now let me very quickly draw a few things here. Okay, now let's say this is the light which is like coming out from the coin, right? So now we already know, if a light ray is coming normal, then there will be no deviation, there will be no refraction, right? So basically we already know this concept. Now let's say this medium is denser, this medium is rarer, and if the light ray is, this is the normal light ray, is coming from rarer to denser medium, so definitely when light ray is passing from rarer to denser medium, it is going to bend towards the normal, right? And on the other hand, if your light ray is coming from rarer, let's say denser to rarer medium, then what is going to happen? The light ray is going to bend away from it, right? Now this is something which we already know. So basically it will bend away from it, something like that, right? Now if your light ray is coming perpendicularly, let's say here it is rarer, here it is denser, and let's say your light ray is coming perpendicularly, it is along the normal at that particular place, then there will be no deviation that is going to happen, right? Okay, so very quickly I have made, let's say the light from the coin is coming out very straight here, right? And let's say, let me just make another ray here so that we can understand this. Let's say there is another ray which is coming just like this, right? Okay, so it is incident at point A here. All right, okay, very quickly let me just make the normal here. This is the normal here, right? Now this is your water, right? And water is, and here we have air, and this is the interface, right? This is the interface. Yes, this is the interface, which is like dividing your mediums, right? Water, air. So obviously when I compare water and air, this will be your denser medium and this will be your rarer medium. Yes, right? Okay, great. Now obviously we are traveling from denser to rarer medium. That means your light ray is going to bend away from the normal. Is that a yes or no? It is going to bend away from the normal, right? So your eyes, what your eyes are going to see, your eyes are going to see that your image is somewhere here. Yes or no? Your eyes are going to see that your image is somewhere here. I hope you guys can understand that, right? So your eyes are going to see your image is somewhere here, right? Okay, great. So because of refraction, our real depth and apparent depth happen. So basically, like I said in the previous part of the slide, that from the interface, so let's say this is the interface, from the interface, the distance of the object from the interface is what you call as your real depth. Let me call it RD. And from the interface, the distance of your image or the apparent, apparent image is what you call as your apparent depth. Is that a yes or no? All right, great. Now there are a few things which we have to understand before doing this particular topic. Let me just very quickly say important things to keep in mind. Now what are the important things you have to keep in mind? All the measurements are taken from the interface, right? So whatever measurements that we will do, we'll always do it from the interface. So like I said, from the interface we are talking about the real depth. From the interface we're talking about the apparent depth. The distance between from the interface to the real object is what you call as your real depth, and the distance between from the interface to your apparent image is what you call as your apparent depth, right? Okay, great. Next thing, the medium from where the light is coming is what you call as the refractive index nu2. Okay, so you guys can see your light is coming from water and it is reaching your eye. Yes or no? So let me say refractive index of water is some nu2, and next line is the medium in which the light is going is nu1, has refractive index nu1. That means this air has a refractive index of nu1. I hope that is understandable, right? Okay, now one more important thing that you have to understand. Now important is because these rays, let me say this ray is very close to the normal. And there's a reason for that, right? There is a very good reason for that. I will make you guys understand why I'm saying that that ray is very closer to the normal. Why? Because let me explain why the ray is very closer. Because we are going to do an assumption that your angle of incidence and angle of refraction are very, very small. Now that can only happen when your rays are very close to your normal. So if your ray is very close to your normal, what is going to happen? Your normal will be very, very close and the angle that is made will be very, very small. If they are very, very far away, the angles will be big. That is the reason, right? So in order to do that assumption that your angle of incidence and angle of refractions are small, we say that this ray, I'm talking about the ray which is like reaching your eye, that ray should be close to your normal. Is that a yes or no? Right? Okay, great. Now let me very clearly see here which is your angle of incidence. This is your angle of incidence and this is your angle of refraction. Is that a yes or no? I hope you guys can understand that, right? Okay, great. So if that is understandable, very quickly let me just name everything. So this point is B. All right, let me say this point is O. Okay, all right, where the image is, let me say this is my eye, right? Okay, great. Now let's try to find out if there is any relation between your apparent depth and real depth, right? Okay, so before I do that, I really want this diagram back there, so I'll just try to copy it as much as possible. Copy, right? It will not be a perfect copy, but still you guys can understand that. Okay, yes. All right, let me just make it smaller. It can fit here. All right, great. Now what I'm going to do here, I'm going to apply Snell's law, right? Now where I'm going to apply Snell's law, I'm going to apply Snell's law at point A, right? I'm going to apply Snell's law at point A. So at point A, let's apply Snell's law. All right, so at point A, when I apply Snell's law, so here basically I'm applying Snell's law, so I can write nu1 times sine of r will be equals to nu2 times sine of I. Is that a yes or no? Right? Okay, I hope you guys can understand that, right? Okay, very great. Now let me just write that down. Nu1 times sine of r is actually equals to nu2 times sine of I. Is that a yes or no? Pretty simple, right? Okay, great. Now as I said, like I said, that this line is close to the normal. Which normal I'm talking? I'm talking about this normal. So these two lines are very, very close. So if they are very, very close, if the lines are very close, then I can simply say angle of incidence and angle of refractions are also very small. Yes, yes, that will also be very small. I hope you guys can understand, right? Now if you guys remember, for smaller angles of sine, sine and as well as tan, the angle comes as the answer. For example, if I say sine of 0, what is the answer? Answer is 0. So basically for smaller values of sine, angle comes as the answer. Very similarly, if we have tan 0, the answer comes to be 0, right? So if the angles are small, the angle itself comes to be the answer. I hope you guys can understand, right? So if it is written sine I, if the angle is small, that is angle of incidence is small, it can be written as I or it can be written as tan I. I hope you guys can understand. Very similarly, if it is written sine R, if the angle is small, you can write it R or you can also write it tan R. Yes or no? Very important, right? Okay, so what I'm going to do here is I'm going to write it, instead of sine I, I'm going to write it tan I. Instead of sine R, I will write it tan R, right? So in this equation, I will write nu1 times of tan R, that must be equal to nu2 times of tan I. Yes, I hope you guys can follow, right? Now let's look at the diagram. This is angle I. Is this be also angle I? I hope you guys can see that this will also be angle I. Why? Because alternate interior angles, because you guys very clearly see this is making a Z. This is angle I. This must be also your angle I. I hope you guys can understand that. Yes. Okay. So if this is a line and you guys can see there are two lines. So if this angle is R, then this must also be R. Yes or no? So I can write it. This is also your R. I hope you guys can understand that, right? Okay, great. Now let's talk about, if I talk about triangle OAB, right? So in triangle OAB, now look for triangle OAB. So where is your OAB? Here it is, OAB. So in triangle OAB, what is the value of tan I? What is the value of tan I? In triangle OAB, what is the value of tan I? Tan I is basically a ratio of perpendicular upon base. Now you tell me, where is your perpendicular, where is your base? This is the triangle here. right? Here is the angle. So this will be your perpendicular AB. Yes or no? So let me write that AB. And what is your base here? If you see, this is the triangle, right? This is the triangle. This is the perpendicular, then this must be the base, that is OB. Is that a yes or no? OB is the base. I hope you guys can understand that, right? Okay, very nicely. Let's look at different triangle now. In triangle ABI, right? Now just find ABI here. Yes, ABI, this triangle I'm talking about, right? This triangle is right angle at B. I hope you guys can see that, right? Okay, so in this triangle, look for tan of R. Tan of R can be written as perpendicular upon base. Now you tell me where is your perpendicular and where is your base in this particular triangle, right? This is your angle R. So your AB is perpendicular, right? And BI is the base. I hope you guys can see that. AB is perpendicular and BI is the base. Is that a yes or no? All right. Okay, great. Now substitute these values, substitute it here, right? Substitute these values here. So when I substitute this value here, you will get nu 1 times of tan R. Now remember, what is tan R? Tan R is this value. Remember that, right? So this is AB upon BI, and that is equals to, yes, nu 2. What is your tan I? Tan I is this value, right? So just put that here, AB upon OB. So your AB and OBs will cancel out. Now let's look closely. What is your BI and OB? What is your BI? If you clearly see, BI is basically your apparent depth. Is that a yes or no? BI is basically your apparent depth. So this is nu I multiplied by apparent depth, AD. And what is your OB? Look closely. What is your OB? OB is basically your real depth. Yes or no? So OB is basically your real depth. So clearly you can see there is a relation. Now what is the real relation? Real depth upon apparent depth is actually equals to nu 2 upon nu 1. I hope you guys can understand, right? Or you can simply say nu 2 upon nu 1 is actually equals to real depth upon apparent depth. I hope you guys can understand that, right? Now before we conclude this, you have to understand what is your, from where you actually calculate your real depth and apparent depth. Real depth and apparent depths are calculated from the interface, right? From the interface you calculate these values, right? Secondly, what is the refractive index? Nu 2 is the refractive index of that medium from which your light ray is going out, or from which the light ray is coming, right? So that is the refractive index, right? And what is nu 1? Nu 1 is the refractive index of the ray which is going out to the second medium. So this is the refractive index of your second medium, right? So for nu 1, the medium in which the light is going, nu 2, the medium from which the light is coming. I hope you guys can understand that, right? Now there is one more thing which we have to understand here. We have to talk about something which we call as normal shift. So the shift, you guys can see there is a shift here. We call this as normal shift. Right? So normal shift, you can simply say, you can call this as some t. Normally it is represented by the symbol t, right? Or you can simply say normal shift, right? That is by how much length your image is shifted with compared to your object. So basically this here was the object and is shifted by this particular amount. So how you can calculate? It's pretty simple. You have to subtract your apparent depth from your real depth, then you will get that value, right? So your normal shift, let me just write it here, normal shift. So your normal shift is basically, if you see it from the image, it's real depth minus apparent depth. Yes, I hope you guys can understand. It's real depth RD minus your apparent depth. Yes or no? Right? Okay, great. So here, from here, you can simply say apparent depth can be written as, from this particular formula, apparent depth can be written as nu 1 upon nu 2 times of your real depth. Is that a yes or no? You can write it like that. Okay, so if you can write it like that, just write it here. Real depth minus nu1 upon nu2 times of real depth, or you can simply say your normal shift ns is actually equals to, take your real depth common, and this will be equals to 1 minus nu1 upon nu2. Now remember, what is this nu1 upon nu2? You have to understand nu1 is the refractive index of that medium from which the light is going, and nu2 is the refractive index of that medium from where the light is coming. I hope you guys can understand, right? So this is how you can define it also, right? So your normal shift is actually real depth 1 minus nu1 upon nu2, right? Okay. Now let's look at some questions so that we can understand the concepts better. So question number 1, let's look at that. A rectangular glass slab rests in the bottom of a trough of a water. A ray of light incident on water surface at an angle of 30 degree passes through water into the glass. Calculate the angle of refraction in the glass given that nu for water is 4 upon 3 and that for glass is 3 upon 2. All right, great. Now this question is telling that we have a rectangular glass slab rest in the bottom of a trough of water. All right, so we have, let's say we have this water tank like thing, right? And in this we have water till this particular place, and there is a glass slab which is like resting here. All right, okay, great. Now according to the question is saying a ray of light incident on water surface at an angle of 30 degree. So here you have a ray of light which is like incident on the water surface. So this will be the normal, and this angle is 30 degree which is given in the question, right? Okay, passes through the water into the glass. All right, great. Now from here obviously it will deviate closer, something like this, yeah, right? Okay, so here there will be normal and it will deviate even closer, something like this, right? Okay, great. So the question is asking that passes through water into the glass, calculate the angle of refraction in the glass, right? So basically the question is asking us to find out this angle. What is this angle? Angle of refraction. This is something which this question is asking us to find, and there are a few things which is given to us. What are the things? Given that nu of water, so you have refractive index of water is given to you, that is 4 by 3, and refractive index of glass slab is actually given to you 3 by 2. Nu of glass slab is given to you, that is 3 by 2. All right, okay, great. Now obviously whatever this angle is, this will also be that angle, right? So let's first find out this angle. So in order to find that angle, we will apply Snell's law at point A, right? So very quickly apply Snell's law at point A. So when you apply it, you can simply see, okay, now here we have air, then we have water, right? And then here we have glass, right? There are basically 3 medium. So basically we are going from air to water for that refraction at point A, and we are applying Snell's law. So refractive index of air, let me call it refractive index of air, multiplied by sine of angle 30, that is equal to refractive index of water multiplied by sine of R. Yes or no? All right. So refractive index of air is, like we already know, that is 1. What is the value of sine 30? Sine 30 has a value of half. This is refractive index of water multiplied by sine of R. Now refractive index of water is also given to us, that is 4 by 3. I'll just write that here. 1 upon 2 is equals to 4 by 3 times of sine of R. Is that a yes or no? So from here I can say sine of R is coming out to be 3 upon 8. Is that a yes or no? Sine of R is coming out to be 3 upon 8, right? So let's just remember this value. All right, let's move forward with the question. So I know this part also. Now I'm supposed to find out what is this angle of refraction, right? Let me call it R dash. All right, okay. So let's say this is point B, so we will apply Snell's law at point B also, right? So apply Snell's law at point B, right? So apply Snell's law at point B. So when I apply Snell's law at point B, this will be, yes, so from here I can see refractive index of water times sine of angle R will be equal to refractive index of glass times sine of angle R dash, right? I'll just write that thing here. Refractive index of water times sine of angle R, that will be equal to refractive index of, yes, glass times sine of R dash. Yes or no? Okay, refractive index of water is given to me in the question, that is 4/3, right? Sine of R, we already knew that is 3/8, will be equal to refractive index of glass is also given to me in the question, that is 3/2, right? Okay, all right, 3/2, and sine of R dash is something which I have to find out, right? So this will become 2, this is gone, so this will be 2/3 into 2. This will also cancel out, so you will get sine R dash. So from here I can find out R dash will be equal to sine inverse 1/3. So I know this value and this is that, right? I hope you guys can understand that, right? Okay, let's move to our next question. Question number 2. Question number 2 says that a ray of light is incident at an angle of 60° on one face of a rectangular glass slab of thickness 0.1 meter and refractive index 1.5. Calculate the lateral shift produced. All right, okay. Now, what is the value of lateral shift? P is equals to, T is the thickness, sine I minus R upon cos R. This is the value of lateral shift. We remember, we just derived it in the starting part of the video. All right, okay. Now a ray of light is incident at an angle of 60°. So we have a rectangular glass slab. All right, so you have a light which is like incident here. All right, okay. So let's say this is making an angle 60°, right? We are going from rare to denser medium. It will bend towards it, there will be some angle of refraction and it will come out something like that. Yes or no? Right? Okay, so there will be a lateral shift. This is something we are supposed to find. This is P, which is given by this, right? Okay, great. Now first thing first, you are given that this distance is 0.1 meter, right? And refractive index is also given to you, that is 1.5. Great. Calculate the lateral shift, right? So in order to find out lateral shift, the things, this is given to me, right? Now angle of incidence is given, but angle of refraction is not given. So this is something which we have to find out. So angle of refraction you can easily find out. Let me say this is where the light is incident, right? So apply Snell's law at A. So apply Snell's law at A. So when I apply Snell's law at A, I can simply write it here. Nu of air times sine of 60° will be equal to nu of glass multiplied by sine of R, which is something which I have to find out. Nu of air is basically 1, sine 60 is √3/2 is equals to nu of glass is given to me 1.5 times of sine R. Yes or no? So basically you will get sine R is coming out to be, yes, this is half into √3 divided by 1.5, right? Or I can simply 1.5, I can write it 3/2. So instead of 1.5 I'll write 3/2. This is 3/2. 2 and 2 will cancel out, so you have √3/3, or simply just multiply it by √3/3. You will get 3/3 or 1/√3, right? So your sine R is basically equals to 1/√3. All right, this is something which I already know here, right? Okay, now all I have to do is, so I basically know the value of R also. So R is actually equal to sine inverse 1/3, right? So just now put this value in the formula, right? So your formula is P is equals to 0.1 multiplied by sine of angle I. Angle I is given to you 60 minus R is also given sine inverse, right? if you see this approximately comes out to be some 35 something, right? Has some value of like that. You can just find that out. All you have to do is put this value over there and you will get the value of P, right? Just do the calculation, you will get the value of P, right? I hope that's understandable. Let's move to the next question, right? Question number 3. The apparent depth of an object at the bottom of the tank filled with a liquid of refractive index 1.3 is 7.7 centimeter. What is the actual depth of the liquid in the tank? So the apparent depth of an object at the bottom of the tank filled with a liquid. Okay. So apparent depth of an, let's look at question number 3. Question number 3 is saying the apparent depth of an object at the bottom of the tank filled with a liquid of refractive index 1.3 is 7.7. So apparent depth is given to you. AD is given to you. That is 7.7 centimeter. What is the actual depth, right? So basically you have an object, right? And which is like at the bottom of the tank, you have a tank which is like filled with water, right? Okay, and obviously the image is somewhere here. So this distance is given to you 7.7, right? This distance is something that is your real depth, which is something which you have to find out, right? Now you are given the refractive index of this liquid, that is 1.3. This is nu 2, this is nu 1, right? This is basically air, so this will be having a refractive index of 1, right? Okay, now we already know real depth upon apparent depth is actually equals to nu 2 upon nu 1. Yes or no, right? So apply the formula here. Real depth is something which I have to find out. Apparent depth is given to me 7.7 is equals to nu 2 is also given 1.3 and upon 1. So this real depth will be equal to 1.3 into 7.7. Just do the calculation. This is 7.7 upon 1.3, 7321, 7321. This will be 230177, right? 1, 10, again 10. So 10.01. Real depth will be equal to 10.01 centimeter. I hope you guys can understand that, right? Okay, let's move to the next question. The velocity of a the velocity of a light in the glass is 2.2 into 10 to the power 8 meter per second, and that in air is 3 into 10 to the power 8 meter per second. By how much would an ink dot appear to be raised when covered by a glass plate 6 centimeter thick? All right, great. So basically you have ink, right, and at some place, right, and there is let's say a thick, it's written you have a thick glass plate which is like kept on it, right? Because of that, so when you see it from here, let's say from here you actually see, so when you see it, obviously this drop is going to be appearing somewhere here. Now this is something which you have to find out, okay, that how much, by how much length it is being, it is being raised, right? That is something which question is asking us, right? So in order to find that out, we need a few things. First of all, refractive index we need. Now we do not know the refractive index, but one thing is given to us, that is the velocity. So from velocities we can find out the refractive index of this material, right? So let's do that. And also this is also given, 6 centimeter is the thickness of this plate, so this is also given to us. So very quickly I can find out the refractive index. Now we already know refractive index can be found, so refractive index of glass upon refractive index of air, or I can simply say refractive index of glass with respect to air is given as velocity of light in air upon velocity of light in glass, right? So this will velocity of light in air is 10 to the power 8 meter per second, and velocity of glass is 2 into 10 to the power 8 meter per second, right? Meter per second. So you cancel these things out, so you will get refractive index of glass with respect to air is actually 3/2. So this is now given to us, right? Okay, great. Now we have to just very simply find out apparent depth and real depth, right? Okay, now you guys can see real depth is actually 6 centimeter, right? Apparent depth is something which I have to find out. Apparent depth is something which we can find out. So basically I can use the formula real depth upon apparent depth is basically equals to nu2 upon nu1, right? So nu2 is basically refractive index of glass with respect to air, and nu1 is refractive index of air, right? So I'll just simply write that out. Real depth upon apparent depth is basically equals to refractive index of glass with respect to air upon refractive index of air. Yes or no? All right, great. So real depth is given to you, that is 6 meter. Apparent depth you do not know, write it like that. Okay, so this is 3 by 2, right? Or you can simply see your apparent depth will be equal to, so from here you will apparent depth will be equals to something like this. This is 3 2, your apparent depth is basically 4 meter, right? 4 meter is your apparent depth. Now what is, by how much it is being raised? So basically you're supposed to find out this distance, right? And that you can, that is basically your normal shift, right? So your normal shift is real depth minus apparent depth, right? So what is your real depth? Real depth is basically 6 centimeter minus apparent depth is 4, so 2 meter is the answer. So basically you will see the ink is raised by 2 centimeter, right? Ink will be raised by 2 centimeter. I hope you guys can understand that, right? Okay, so that's all for today. Thank you and have a nice day.